Okay, so I'm not there today, but we do want to continue taking a look at our unit on measurements. And yesterday we, at the end of class, talked a little bit about the need for a consistent system of measurement. And so in the sciences, we have adopted the metric system, like as we talked about yesterday. This is a system measurement based in powers of 10. So today we're going to talk about how to take a proper measurement in science for recording data for the lab. Ultimately, the goal is to get the most precise measurement possible, the most reproducible measurement possible. And so, as far as what you need to do today, follow along, highlight everything, record down the notes, the information, the examples that we're doing, and I'll be checking that tomorrow at the start of class. So when it comes to taking a proper scientific measurement, the most difficult part is to determine how many digits you need to record. Well, in order to figure that out, we're going to have to understand the design of the measuring device. Like, what values is it able to tell us? Because ultimately, to get the best proper scientific measurement possible, we want to record all known values that the measuring device can tell us, plus one digit that is uncertain. So as it says here, when we record it, we're going to have one value that is uncertain, is our uncertain digit, meaning an estimated value. We want to get as many value places as possible from our measuring devices so that we get the most precise measurement possible. Now, in order to do that and how that works, it's going to depend on the measuring device that we're working with. Okay, the number of digits and the values for those digits is going to depend on the measuring device itself. So in order to do this, there is a systematic way in order to determine the scale, the values, all that sort of thing. And so that information is given here on this slide. This is a super important slide. You might want to put some big stars around it, put a big highlighted box around it, something, because you're going to be coming back to this slide over and over again until you develop this skill. So how do we tell how many digits should be recorded in a measurement? Well, first off, we have to identify the minimum scale on the measuring device. So when you look at any measuring device, whether it be a ruler, a graduated cylinder, anything, what does every little mark, what is its value? What value place does it measure? What number would go in that value place? What is the minimum scale of the measuring device? And then once we've determined the minimum scale, we need to look at what kind of scale is it? Is it a power 10 scale or not a power 10 scale? If the scale increases by a power of 10, meaning does each line on the scale go up by 100? Does it go up by 10? Does it count by ones, by 0.1, 0.01? In other words, some multiple of 10 or some division of 10. If the scale goes by a multiple or division of 10 as a power 10 scale, we can then estimate one digit beyond that scale. So if the scale measures to a whole number, the ones place, we can then estimate the next value place, which would be the tenths or the first decimal place. Now, if the scale increases by some other amount, like the examples here, if each line goes up by 150 or 30 or 5 or zero point 0.2, then it's not a power 10 scale. And then where we end up putting in our estimated digit is going to be in that last value place represented by the scale. Out of the two, the first one is preferred. It gives us the most precise and hopefully the most accurate representation of the measurement versus these other scales, which are not power 10, generally not quite as precise. So for example, we have a centimeter ruler here depicted on the screen. And when we take a look at it, we can see we're counting up by whole numbers of centimeters, 1, 2, 3, 4. But then in between each of those, we've got 10 little markings showing that our scale here is to 0.1 centimeters. Okay, every line on the centimeter ruler goes up by 0.1. So 0.1, 0.2, 0.3, all the way up to 1, and then continues on from there. Now this would be a power 10 scale. So if we were going to take the measurement of this red line that I added in, we can tell from looking at this that the red line is at least 3 centimeters, but is less than 4. We can also tell that because each line is 0.1, that we're past 3.1, past 3.2, 3.3, 3.4, 3.5, but not quite to 3.6. So we know that the measurement is at least 3.5. We know that. But there's still a little bit more to that arrow tip that's in the space in between. And we don't want to round things off. We don't want to cut things off. We want to get the most precise measurement possible. So because this is a power 10 scale, we can estimate to the next value place. Now, what we put in that estimated spot is going to depend on how much of the gap we think we've extended into. You kind of have to picture in your mind's eye that that gap is broken into 10 parts, and how many of those 10 parts would it be covering up. Now, it's an estimate. Okay, so we don't have to be exact here. We can estimate, but of course we want to make a good estimate. So when I look at this, it looks like it's less than halfway, so I'm going to say 3. 3.53, and of course we want units of centimeters on that. So, but because it's estimated, you could say, well, maybe it's 3.52 or 3.54. Those are all fine values for this measurement. The important thing is that we agree on the known values, and we're just estimating that one extra value. A couple more examples here. If we take a look at the arrow on the right-hand side, this is the same centimeter ruler. We can see that we're beyond 27, but not quite to 28. We can see that that arrow is beyond 27.1, but not to 27.2. So if we were going to take a measurement of this, we should all agree that we have at least 27.1. So such as in the highlighted examples here, 27.17, 27.18, 27.19, just that last additional value place. Because again, this is a power 10 scale. It's giving us values known to that first decimal. We can then estimate the next decimal place after that. So those would all be good measurements for this. If you were in the lab taking replicates and you and your partners came up with those 3 measurements for this line, those would be great replicates, very precise. Now, the other example on the left here, that arrow looks like it's right on top of the 19. So we already know from the previous examples that this centimeter ruler measures to the first decimal place. So we have to have that first decimal place in our measurement. And also because it's a power 10, we have to estimate the next value place after that. But it looks like we're right on top of the 19. Well, we know it's 19, and we know it's not 19.1, so we can have 19.0. But if it looks like it's right on the line and there's no need to estimate further, then we could say it's 19.0. So we got 19.0 for the known, and then a 0 after that, so 19.00. And it still gives us the same level of precision as our other measurements. So let's do a couple of practice examples together. And anytime you get a brand new measuring device that you haven't worked with before, this is the step-by-step of how to determine the proper measurement for that device. So first thing is, what does each line on the scale represent? So here's what I like to do. I pick a number on my scale, such as the 100, and what's the next number that I can read? In this case, 150. So that tells me that I just went up 50, and this is kilograms on this scale. And then I count how many lines in between those two numbers. 1, 2, 3, 4, 5. So that's 5 lines. Which tells me that my scale here is 10 kilograms for each line. So every line on here is 10 kilograms. Next step, is that a power 10? Yeah, it's a power 10. I mean, the scale is 10. So that tells me then that if I were to get some room to write here. If this is 100, then the next line is 110, and the next line after that is 120. So what is the best value that can be reported for my arrow? Well, I know it's 110, but I know it's less than 120, so we'll start with 110. We know the hundreds and the tens. I mean, my scale is fluctuating in the tens, 110, 120, 130. So since my scale is counting by tens, my next value place that I would estimate is this one spot. So the question is, it's not 110, what is it then? Well, here again, we have to picture what we think. If we broke the little gap here into 10 pieces, how many pieces are being covered up? And so when I look at that, I think that that is a 3. So 113 kilograms. Remember that 3 is estimated. I don't know that it's 113. I just know it's at least 110. Now, could we say 112? Yes. Could we say 114? Yes. Those would all be good estimates. But this gives me, again, the most precise measurement for what's being indicated here on this scale. The next example, we're going to do the same thing. I'm going to start at 0, go up to 25. And so we've just increased by 25 liters. And then how many lines in between? We've got 1, 2, 3, 4, 5 lines. And so that's 5 liters per line. Now that is not a power 10 scale. We're not counting by some power 10. We're not dividing by some power of 10. Here we're counting by 5s. So that means we're going to have to look at rule number 2 from that previous slide. The 5s, that is going to be fluctuating in that ones place. So 5, 10, 15, 20, 25, we're going to keep alternating in that ones place. And so that's going to indicate the last spot that I can have in my measurement. So if I take a look at then my scale over here, I've got 25, 30, 35, and there's my 40. Well, I know that I have got at least 35, but less than 40. So I know this. But I need to estimate. And again, my scale, because I'm counting by 5s, is changing in this ones place right here. So I know it's more than 35. I know it's less than 40. I can't go 35 point something or even say 38 point something, because if I put an 8 in this spot, that 8 is going to be estimated. Like, I don't know that it is exactly 38, but based on where my marking is right there, that to me looks like it could be 38, and that'd be 38 liters. So all known values plus 1 that's estimated. That scale was fluctuating in the ones place. I have to estimate that 8, and so therefore that's where my measurement is going to stop. And that's the best measurement for this. Because it doesn't let us add an extra value place like the previous examples, that's why these scales are not necessarily as precise as the ones that are power 10. And here's our last example. This time we're going from 0 up to 0.05. And this is centimeters. And we're going up by 1, 2, 3, 4, 5 lines. 0.01 centimeters per line. And so this is a power 10. Okay, we have 1 100th. So we're dividing by a power of 10, but it still makes it a power of 10 scale, which is going to allow us again to record our measurement and then add an extra value place. So if we take a look here, we've got 0.01, 0.02, 0.03, so 0.03, and we know the next line is 0.04, that line there. So I know for sure that my measurement is 0.03. I know that for sure. But now, because it's power 10, I can estimate into that next value place. And again, now I've got a picture. I'm breaking that into 10 parts. Exactly what that would be. It's pretty high up there. I'm going to say an 8. So 0.038 centimeters. I know it's at least 0.03. It's less than 0.04. I'm estimating that 8 because I can go to the next value place since it's a power 10 scale. And that's going to give me the best, most precise measurement that I can get from this scale. Okay, so that gives us half a dozen examples that we can look at and cover again tomorrow. Again, your task for today was to get those notes, get those examples in your note packets. I want to be taking a look at that tomorrow when I come back to class. And then tomorrow we will also be looking at more examples so we can get more practice at this. This is a skill that we're going to be working on developing over the next couple of weeks, because as we then get deeper into the year and doing more labs and taking more measurements, we're going to be looking for proper scientific measurements as we go forward, because we want to get the most precise answers and hopefully therefore the most accurate as well. So make sure you have all of that, and we will come back again tomorrow.